Good morning, everyone. I welcome you all to the joint workshop between HUA and BITS-Pilani. I am S. Srikanth, a PhD scholar who is working under the supervision of Dr. Arshad, Javed and Dr. Sanket Goel. I would request Professor Sanket Goel to speak a few words about the workshop. Sir.
Thank you, Srikanth.
Yes.
Very warm good morning to all of you. In Japanese, we say konnichiwa ohago. I hope that I did not misspell. In Hindi, we say suprabhat and namaste. My name is Sanket Goel, and I am from BITS-Pilani. First, I would like to thank Professor Souvik Bhattacharyya, our Honorable Vice-Chancellor, to be able to come to this workshop. I also welcome Professor Shin-ichi Tate, who is the Executive Vice President, Office of Academic Research and Industry, Academia, Government and Community Collaboration, Hiroshima University. I also welcome Professor Sudhirkumar Barai, Director, BITS-Pilani, Pilani Campus. I welcome all our esteemed dignitaries to the inaugural session of the first workshop during this year 2020 between BITS-Pilani and Hiroshima University. Thank all the esteemed speakers for sharing their precious time to join this workshop. As we know that BITS-Pilani and Hiroshima University have been collaborating for the last several years. As part of this sustained collaboration, advanced core of energetics from Hiroshima University and Microfluidics and Nanoelectronics Lab from BITS-Pilani developed the idea to conduct this workshop. I extend again my heartfelt welcome to all the speakers and participants for joining this event. I hope that more participants will be joining subsequently. Specifically, I am grateful to the speakers from both sides, Professor Nishida, Professor Matsumura, and Professor Hongliang from Hiroshima University, and Professor Dubey, Professor Roy, and Professor Javed from Barai for agreeing to present their work and explore the futures of collaboration. I'm delighted to mention that this workshop is being organized with an unparalleled support from Japan India International Linkage and University and International Program and Collaboration Division, that is IPCT from BITS-Pilani. To begin the inaugural session, first and foremost, I request our Vice-Chancellor, Professor Souvik Bhattacharyya, to enlighten us and share his valuable remarks. Professor Bhattacharyya, thank you.
Thank you, Sanket. Ohio gozaimasu, Hiroshima, from Pilani, India. Greetings and good morning to Professor Shin-ichi, Tate, and all other dignitaries from Hiroshima University, Professor Barai, Director of Pilani Campus, BITS-Pilani, and other colleagues and students from BITS-Pilani. So it's been 5 years, Hiroshima Friendship started, formally signed in 2017. The ILDP, the International Linkage Degree Program, under that banner, it has been a very, very generous support that HU has extended to, initially to Pilani campus. Now we have extended to Hyderabad campus in a very organized manner. Several exchanges have taken place. Three batches of cohorts of students have visited Pilani, and many of us, many students and faculty colleagues have been, paying the visit and all that. We've been taken care of so well. It has been a wonderful, enriching experience while we were in Hiroshima campus. In March 2009, you are looking at that photograph. Professor Mitsuo Ochi, President Mitsuo Ochi, and I signed an agreement on jointly supervised PhD. And maybe we can look at the second photograph where I am with. So those are very fond memories and wonderful connects and friendships. I think if you connect on personal levels, the leadership connected, and good things do happen as it's been happening. I know we can do even better, so that's going to happen. IPCD, the International Programs and Collaborations Division of BITS-Pilani, they hosted a group of students and faculty members from HU, also from University of Texas at Austin, and Indian Institute of Management, Ahmedabad, for the conduct of Keiya on-site training program during the 8-9 days of February earlier this year at Currently, the MEMS microfluidic Hyderabad campus and the Smart Robotics Lab of Hiroshima University. Development of high-speed vision-based fluidic devices for biosensing applications is a very exciting area. I hope the complementary skill sets of both the partners are coming through and we do something really, the outcomes are really useful to the industry, to the society, and the research goes on in a very eminent manner. This has been quite productive with mutual visits, joint PhD and publications, this collaboration with the MEMS microfluidics and nanoelectronics lab and Hiroshima's smart robotics lab. To further extend the collaboration, I think Professor Sanket Goel mentioned the Advanced Core for Energetics lab of HU and the MMNE lab are exploring further collaboration in additional areas such as renewable and sustainable energy, also Western value domains, and this workshop that we are inaugurating now aims towards building and nurturing prospective further collaboration in these areas. Maybe we will identify even other areas of working together. I sincerely hope that the Hiroshima-based friendship, the warm friendship continues productively. I thank Hiroshima University leadership and the entire colleagues and the office of ILDP profusely for supporting BITS-Pilani and this endeavor for the last 5 years, I would say. And let us hope that we continue to do quality work leading to eminent outcomes. Hope this workshop leads to identification of niche areas where these two organizations, two institutes can work together and find mutually interested faculty colleagues on both sides. That's very important. We need to have individuals connected. I also hope this is something we had discussed during my visit to Hiroshima in extended meetings over hours. I hope which hasn't happened, the academic twining in undergraduate or postgraduate programs that ILDP raised at length during my sessions I mentioned. In spite of the language and scheduling issues that we had discussed, and I guess those get sorted out, and we have a twining program. BITS-Pilani is very proactive to support that. I'll be happy to revive that discussion if Hiroshima is ready to pick it up. Incidentally, Professor Barai, Professor Sudhirkumar Barai, who is present now, will hear from him. He is now the director in charge for internationalization of BITS-Pilani. So he is the single point of contact, if you will, if Hiroshima wants to connect on internationalization matters. I request Professor Barai to look into additional opportunities that we can explore for the Hiroshima-BITS relationship to flourish in the near future. And also, last but not the least, thank you, Ms. Takihara, the University Education Administrator, ILDP Office, Hiroshima, for your continued support. I remember how you had facilitated all these visits and during our stay and all the meetings and lots of energy. So thank you so much. And once again, we really appreciate the collaboration efforts that have been and the support that have been extended from the Hiroshima side. And I urge BITS to continue to put in the efforts and let us look at very, very valuable and eminent outcomes out of this research collaboration.
Thank you very much, sir, Professor Bhattacharyya, our Vice-Chancellor, for enlightening us. We can assure you that we'll further take this collaboration to the next level and will nurture it in a great manner. Now I humbly request Professor Shin-ichi Tate, the Executive Vice President from Hiroshima University, to kindly educate us with his precious thoughts. Professor Tate, please. Thank you.
Can you hear me? So I think the microphone.
We can hear you, sir. Go ahead.
Okay, thank you. All right, thank you very much for organizing this workshop. And I also thank organizers and the participants joining in this international workshop between our Hiroshima University and BITS-Pilani. So My name is Tate, and Vice President in charge of research at the Hiroshima University. On behalf of the faculties in this university, I will give you a few words before starting this workshop. So delegates from BITS-Pilani have a lot of introduction of this workshop, and I understand their expectation for a validation step in future. So this workshop, I realize this is aiming to get the collaboration between our university and your universities. And I know that BITS-Pilani is one of the leading edge universities in India and have a lot of international collaboration already in the worldwide. And I hope this workshop lead to the collaboration with our university and a candidate of the BITS-Pilani categories. So anyway, for our side, this time we have some very outstanding researchers in the energetic research core. I think so now the energetic issues are very important in the issues of SDGs goals, as you may know. So our delegates in this research core have extensive approaches to the energetic issues. I think their presentation may inspire some collaboration some people in your university. I hope this workshop will become very successful and fruitful to make up a new collaboration between us. Thank you very much. Enjoy your workshop today. Thank you.
Thank you very much, Professor. And we really grateful for your words of appreciation and very crucial suggestions. Finally, for this inaugural session, I urge Professor Sudhirkumar Barai, the Director of BITS-Pilani campus, and we would like to request him to share his views. Professor Barai.
A very good morning to all of you from a cloudy BITS-Pilani. It's a rainy time. We have the cloud over here, but I'm sure this workshop is open up with the bright sunshine of a very strong collaboration. So Professor Shin-ichi Tate, Executive and Vice President of Hiroshima University, Professor Bhattacharyya, Vice-Chancellor of BITS-Pilani, and all colleagues from the BITS-Pilani as well as from the Hiroshima University. I'm very happy to be present during this joint workshop, which is happening virtually because of the post-pandemic situation. But I'm glad that the distance is not very far. We are absolutely virtually connected, and it is indeed a great pleasure to be here for this workshop. As Professor Bhattacharya mentioned about the strengthening the relationship and our friendship and taking it to the higher level, I'm very, very happy that the specific areas researchers have joined hands together and taking it to the next level. And this particular workshop will really lay a very strong foundation, which is already in collaboration, but still we can take it much higher level, and that is going to happen. So I'm very glad that this workshop has been arranged, and definitely we will see some fantastic results coming out from this workshop. To add further, I'm very happy to say that just in July month we had also conducted one international webinar on smart cities beyond the pandemic, and I'm very, very glad to say that among our collaborators, the Hiroshima University, Professor Ayub Sharifi and Professor Fujiwara, they participated and there were fantastic lectures, and there also we are exploring some of the possibilities to have the joint collaboration between BITS-Pilani and the Hiroshima University. To add further, Professor Bhattacharya possibly would have been very happy to share, but I'm just sharing on his behalf that recently the Department of Science and Technology from Government of India, BITS-Pilani has been awarded a very prestigious funding for setting up the Technology Innovation Hub in the area of bio-CPS, bio-cyber physical systems. And as we know that the Hiroshima universities in that segment has been continuously working in this domain, it would be fantastic to collaborate on that front as well, because this is something where not only in the area of research, but also innovations and the creating an entrepreneurships and so on. The learning from either side of it will really take it to this particular innovation hub to a different level. So I wish all the best to this workshop, and I'm sure some fruitful things will come out during this workshop. So thank you for inviting me, for being here for the inaugural part of this workshop. Have a wonderful day. Thank you.
Thank you, Professor Barai, for your inspirational views, especially mentioning that we have been awarded this high-end cyber physical system grant from DST. So with this, we would like to thank all our esteemed dignitaries for sparing their time for this inaugural session. Thank you very much. Arigato gozaimasu, as they say, and dhanyavad from India. So now we should start our sessions or topics of the workshop. First one is will be given by me and followed by Professor Nishida from Hiroshima University, Professor Banasri from BITS-Pilani, then Professor Matsumura from again Hiroshima University, Professor Arshad Javed from BITS-Pilani, and Professor Hongliang from Hiroshima University. Finally, Professor Dubey from BITS-Pilani will be sharing his thoughts. So I will be starting primarily sharing what's going on as the overall development on the MEMS microfluidics and nanoelectronics domain, and what kind of collaboration interests which we can foresee in time to come. So here I'm sharing my slides. Srikanth, you may have to. Okay. Yeah. So I hope you can see my screen. All right. So we have MEMS microfluidics and nanoelectronics lab in the Hyderabad campus of BITS-Pilani. We started this lab around 3 years ago, and now we have work going on in diverse domains of this area and as well as the other ancillary areas. So we have faculty members from a couple of departments in the campus, and also the lab supports research work from other departments as well. And just to mention that we are also collaborating with other 2 campuses and other institutes as well in India and as well as outside India. Just to give you a snapshot, we have currently 1 postdoctoral fellow supported by 1 lab technician. Also, we have close to 19 full-time PhD candidates. Around 2 or rather 3 candidates have completed their PhD work. Besides that, several postgraduate and undergraduate students have also completed their project work or their thesis work. We also have 3 part-time students from different organizations. I will show you very briefly what are the work which we are doing. As you can see that our main focus is to develop microsensors, if I can say in 2 words. So these sensors can be used for a variety of applications, and to develop these sensors, different kinds of mechanisms can be harnessed, be it 3D printing, be it printed electronics, or conventional photolithography, soft lithography, and so on. So majority of the facilities are available in the lab or in the campus itself, which not only includes fabrication but also characterizations and testing as well. We have been supported around 3.5 crores, which is rupees, which is like 35 million Indian rupees by different agencies in India. As you can see that these are from diversity of agencies in India. And not to mention that as Professor Barai mentioned, the lab is a very integral part for this bio-cyber-physical system grant which the BITS-Pilani as a university has received. And a lot of work will be carried out under the umbrella of this laboratory. Just to show you a very quick overview of this lab, I have a very brief video and I hope you can see that. Thank you very much for your kind attention. So I'll move on. So I will briefly explain some of the key projects going on in the lab, and possibly that will lead to some of the alignments with the ACE laboratory and our colleagues from Hiroshima University. So one of the initial work which we have been doing to develop a miniaturized discometer, we have tried to use various different mechanisms to develop it. I will be very brief in explaining based on 3D printing. You can see a simple 3D printed microfluidic device which has been developed in few minutes with a cost of a few cents, I would say. This is a turnkey paper-based device which can be integrated with smartphone and of course IoT and cyber physical system-based approach. And finally, this is an image processing-based approach where we can measure the viscosity. Different approaches are catering the needs for different analytes and different kind of results which we are expecting. We have used them for various different applications like biofuel blending detection, milk adulteration, fuel adulteration, and we have also sensed various biological samples like proteins and other kinds of samples. The second project I would like to briefly mention is about the microfluidic-based enzymatic biofuel cell. You can see that again here also we have used different fabrication strategies like paper-based device, as you can see here. We have also tried to sort of put them together to be able to enhance the optical, the electrical power output, and also we have developed various flexible electronics-based devices which can perform as a enzymatic biofuel cell. On the bottom left, you can see a graphene-based electrodes in biofuel cell. On the middle, you can see pencil electrodes. The one on the right, you can see the completely 3D printed based device, and on the right side, rightmost side, you can see a soft lithography based device. So all these devices are catering the need to develop the energy harvesting device, and one of the futuristic purpose is to be able to integrate such devices with the implantable devices, and for that we already have one funded project. Moving on, similar approach, but to be able to harvest energy using microbes. So we have been trying to use the various microbes, not only develop a device, but also integrate it using miniaturized microprocessors, microcontrollers, and of course the cyber physical based systems. So we were able to not only integrate various microbial cells, but also able to generate power and try to understand the water quality monitoring. Also, our fuel cell work is not just limited to microbes and enzymes. We have been trying various chemicals to develop the chemical fuel cell. So this approach is where we are trying to develop an automated device, and we can create the electrodes using pencils. And without using any manual intervention, we have created this in-house made device where we can sketch pencils of different dimensions and different kinds, and which has really given a very good result to us. You can see that how we have tried to harvest energy and try to use it to be able to power various miniaturized devices. Moving on, this project on droplet-based microfluidics, as mentioned by Professor Bhattacharyya, our Honorable Vice-Chancellor, the Sangam Srikanth is working with the Professor Ishi from Advanced or Smart Robotics Lab at Hiroshima University, and we're trying to use the high-speed vision cameras in conjunction with the microfluidic device, all in-house made. Of course, cameras have been developed separately, and we are trying to see how we can create droplets and how we can not only create droplets but use them for different applications. And the applications include cell encapsulation, various rheological studies, and we are trying to move on towards sequencing and drug screening. The next work I would like to mention is on the microfluidic device for electrochemical sensing. We have again tried to use various paper-based device, 3D printed device, inkjet printed device, and so on. And we have tried to use various chemicals, various biological specimens, and we have also used them for supercapacitors applications recently. So our limitation is essentially to use various different other kinds of analytes, and we are really open to discuss with our collaborators from Hiroshima University. We have the capability to develop devices, but we would certainly like to use for other applications. This is another kind of electrochemical approach where we are trying to use the light to be able to sense various analytes. So we call it electrochemiluminescence based platform. So you can see that we are using a simple smartphone which can give or can detect the detection, can be used to detect hydrogen peroxide, glucose, other gases and so on, to much lower than the specified limit by WHO. So those numbers are very encouraging, and we are trying to use this device for other ancillary applications too. The next work I would like to show is how we have developed this small platform for nitride detection, and nitride detection can be done from various sources like blood or urine, and of course the soil and so on. So we have used a simple colorimetric based assay, and this is the in-house based small pump and detection unit, where we can not only pump the reagent but also can detect what's going on inside this small dark box. We have also enhanced this capability for nitride detection to use it for soil or nutrient detection, where we have incorporated the capabilities to be able to measure the pH and conductivity as well. So we have used the colorimetric based assay to detect nitride. Also recently we have done the electrochemical based assay to be able to detect nitride. Last couple of projects, this is essentially to develop a microfluidic based thermal management system. And the idea is that to be able to incorporate various different reactions like nanomaterial synthesis as well as the DNA or RNA amplification. So this device, or in fact different versions of these devices, we have developed in-house, and we have already harnessed these devices for nanomaterial synthesis. And moving on, we are trying to use them for DNA and RNA amplification. The other project is essentially to be able to characterize the solar parameter underwater. Again, we are using the off-the-shelf different kinds of solar panels or solar modules, and trying to understand when they go underwater how overall efficiency changes, and this efficiency can possibly be used for surveillance applications or other naval applications. Last but not the least, I want to mention this project on flexible and printed electronics, which is a slightly newer project, and where we are trying to see if we can use the simple graphene which has been developed by using a benchtop CO2 laser to not only create electrodes but also to create the microfluidic device. So this simple video tells that how such microfluidic devices which has microchannels as well as electrodes can be rapidly fabricated by a simple benchtop CO2 laser. You can see that how the electrodes have been generated and how the top layer has been peeled off. And the laser has again been ablated to create the microchannels. So essentially all those applications where we need both microchannel as well as the electrodes, we can harness such kind of work in a variety of applications. So we have, for last couple of years, we have started working and we have developed various electronic devices like touchpad, liquid level sensor and so on to prove the concept to develop such printable and flexible electronics. Recently, we have developed newer mechanisms to be able to create such graphene based electrodes, and we have tried to use them for supercapacitor or capacitor based applications. And again, like other projects, we are also imbibing it with miniaturized and compatible microprocessors. Yeah, so based on all these work and based on our initial interaction, primarily with Professor Nishida when we have visited his lab, and which is certainly an excellent and one of the top pioneered lab in such area. So we believe that we can possibly work in several domains. And not only our lab in Hyderabad campus, but also there are colleagues from Pilani and Goa campus as well who can add value to their work. Especially if they are working on a bulk devices, we can probably develop some sensors, be it in lubrication properties detection, be it the oil detection, exhaust gas properties, develop the properties of various fuels, gas sensing, fuel cell, C-waste treatment plant, pathogen sensors, biosensing, primarily the fuel adhesion properties, which I have seen Professor Hongliang works a lot. And I have seen some interest in droplet biomicrofluidics as well, and also the vibration testing. So there is a huge niche of areas we can possibly start. We can probably choose one or two areas in the beginning, and we can launch our collaboration from there, like we have done with Professor Ishi, and it has been very, very fruitful over the last couple of years. So although we have seen a video, but just in a nutshell, we have different kinds of facilities to be able to fabricate, design, characterize, and test different kinds of sensors and devices. We have a fully functional centralized characterization lab, which has D&D of the characterization equipments, so we can certainly harness them. So just to conclude my presentation, I would like to mention that we also have class 100 and class 10 clean room in campus, and we can fabricate various photolithography based devices using such facilities. Yeah, so I would like to thank various collaborators which we have, not only from India but other countries as well. And I would also like to acknowledge various funding agencies. Our contact details are mentioned here. So I would like to conclude with this very memorizing pictures from various interactions which we had with the team from the Hiroshima University. And the top left picture is when Professor Ishii visited our lab when we had a lab in a different locality. And then both of us, Professor Dubey and myself, visited Hiroshima University, and the bottom pictures are where we have visited various labs. The one on the bottom left is the clean room or the nano facilities, top class nano facilities we have at Hiroshima University, and the middle picture is when Professor Ishida, he spared his valuable time to show us his laboratory, and the bottom right picture when various students, especially the 3 students you can see on the right, Srikanth, Sohan and Avinash, they have visited Hiroshima University under the Sakura science program, and you can see Professor Ishii at the center. So these are quite memorable pictures. So at the end, I would like to thank everyone for their time, and now I would like to request Professor Nishida to please start his presentation. And also I would like to request other audience to please answer in the text box, and we'll be very happy to answer these questions. Professor Nishida, please.
Yes. Do you hear me?
Yes, we are able.
And how about, where is my screen share? Professor Luo?
Srikanth, can you please help?
So this is PowerPoint. Then I have to set something, screen share.
Yes.
Uh-huh. So hello, do you?
Now just play.
Yeah. So Professor Goel,
Yes, we are all set, sir.
so you see my PowerPoint slide?
Yes, please. Please.
Thank you.
Thank you.
Thank you very much for joining my talk today. I'm Keiya Nishida. Oops. Oh, no laser pointer here. Yes, my name Keiya Nishida. Nishida is my family name. I'm a professor of mechanical engineering, especially fluid engineering, focusing on internal combustion engine related phenomena, and belonging to the Graduate School of Advanced Science and Engineering, Hiroshima University. And my talk entitled Introduction to Hiroshima University Advanced Core for Energetics, HUACE. You can see HUACE. Objectives, research activities, and strategy. So actually, I'm a head of this research institute, Advanced Core for Energetics. So before talking about this HUACE, ACE, I'd like to talk about a little bit about the my university. Talk about Hiroshima University, HE, and also Advanced Core for Energetics, ACE, research initiatives sponsored by Hiroshima University. Actually, I have another two topics: Automotive Research Collaborative Laboratory, ARC Laboratory, sponsored by Mazda Motor Corporation in Japan, and also Strategic Innovation Promotion Program Laboratory, SIP Diesel Team Spray Lab, sponsored by Japanese government. But because of the time limitation, I only talk about these first two topics. So about Hiroshima University, someone from BITS-Pilani visited Hiroshima University, right? For example, Professor Sanket, Goel, have you been here?
Yes, sir. Yes, Professor Nishida, I am here.
Oh, no. Have you been to Higashi Hiroshima or Hiroshima University?
Yes, I have visited twice, and I also visited your lab.
Yeah, actually, I did not remember very well. And you showed the photograph of your laboratory visit, laboratory tour. One of them was my laboratory.
Yes.
I was not in the photograph, I only show my back, did not show my face. So maybe it was not very good. So sorry. Our university logo is this one, and you can see these three leaves. This is a phoenix tree leaves. Phoenix tree is a symbol of no more war, and also symbol for our grandparent generations' effort for rising like a phoenix from the ashes. You know, in the World War II, 75 years ago, that Hiroshima city completely destroyed, but parent generation worked very hard. Now Hiroshima city is very beautiful city, very developed city. So when Hiroshima University was established after the World War II, before the World War II, there are scattered campus and many schools, small schools. But after the World War II, the central government decided to merge the all small schools into one national university. That is Hiroshima University. And now, anyway, this is the university symbol, logo, phoenix tree leaves. Hiroshima University established in 1949. 5 years later, the World War II ended. One of the largest national universities in Japan, with about 11,000 undergraduate students, 4,400 graduate students, and 3,400 staff members. Hiroshima University undergraduate schools, we have 12, from integrated arts and sciences, letters, education, blah, blah, blah. Then, of course, we have the engineering, School of Engineering. And also, graduate schools. We had 11 graduate schools from integrated arts and science, letters, education, then engineering here. But this was until March 2020, this year. Then what happened? From April to 2020, the Hiroshima University had launched the new organization of the graduate schools. That is 4 graduate schools that offer academic and research opportunities in the fields of natural science, humanities, and social sciences. So 4 graduate schools, humanities and social sciences, advanced science and engineering. We are belonging, or engineering schools belonging this graduate school organization, and then integrated science for life, biomedical and health sciences. So before this reorganization, the graduate school were kind of isolated with each other, isolated. So there are not so very intense professor, researcher, student exchange. So after this reorganization, we can exchange more and more in the, for example, this advanced science and engineering, professor, researcher, and students. That is, I believe, one of the policies of this reorganization. Okay. The university established the promising research initiatives. It is a research group of the inside the university. There are many, and one of them, for this pink highlighted one is very interesting because Hiroshima Research Center for Healthy Aging. Yes, I'm a senior already, so I like to do healthy aging. So I want to, I hope this research initiative is great success. Then this is a continued research initiatives. Then this green highlighted is related to the engineering Center for Research on Innovative Manufacturing, for the development of manufacturing advanced machining systems for high performance, how to work with materials, and also Center for Research on Environmentally Friendly Smart Materials. Also, this pink highlighted one is very unique, Hiroshima Active Peace Building Research Institute. So because of the 75 years ago, a very sad memory, we really decided to keep peace, yeah? But how to keep peace? So this research institute, or research initiatives, making the research how to build, how to keep, how to maintain the peace. It's interesting. Yes, then our research initiatives, Advanced Core for Energetics, ACE. Let me talk about this. As you may know very well, Japan sets a high target for greenhouse gas reduction as a countermeasure against global warming, 26% reduction compared to 2013 greenhouse gas emission rates by 2030, coming soon, 10 years, and also 80% reduction by 2050, also coming soon, 30 years. 30 years. So this is 10 years later, this is 30 years later, and this graph shows the CO2 emission year by year from the developing countries and developed countries and developing countries. For the developed countries, almost not increase so much. However, developing countries, China is the main sources of CO2 emission. Also, India is start to expand CO2 emission, and other Asian countries. So, in terms for avoiding the warmer global warming, we have to maintain the CO2 emission. We have to modulate. We have to reduce the CO2 emission. How do we do? So Japan must develop interdisciplinary technologies such as super high efficiency combustion, IC engine, CO2 capture and storage, energy conservation, and the use of renewable energy sources to achieve this target. So setting these major tasks as our final goal, HUH, Hiroshima University Advanced Core for Energetics, was established in October 2016, 4 years ago. And the HUACE, Hiroshima University Advanced Core for Energetics, focuses effort on the research and the development of super advanced technologies of creation, reservation, and utilization of energy fuels, mainly for the transportation sector. First, we focus on the transportation sector, automobile. And HUACE contributes as well for the education, next generation student education, in this field. And so for these 23 professors and researchers joined the research core from Graduate School of Engineering, Science, Advanced Science of Matter, Integrated Arts Science, and International Development and Cooperation. Something wrong. I cannot move to the second slide, next slide. How to do? Oh, yes, now working. So HUACE organization, objectives, activities, and strategies. So there are 1, 2, 3, 4, 5 research group or former graduate schools of Advanced Science of Matters, Graduate School of Science, Engineering, International Arts and Science, International Development and Cooperation. The other professors, scientists, students in these graduate schools or areas work together for HUACE Advanced Core for Energetics. So what do we do? So we develop the advanced technology on combustion, on internal combustion engine efficiency, biofuel production, hydrogen production and storage, nuclear fusion, and artificial solar energy. This one is really long-term research. But one professor is actively working on this area. And also, we, as an HUACE, design a roadmap Hiroshima scenario to integrate improved energy consumption technologies now and in the future to the year to 2050. And also, we do the joint research, education with the university researchers institute overseas. So today's workshop is for one of the purposes of today's workshop is to establish this and the graduate school course special AC program. Then also we cooperate with HIROJIREN, Hiroshima Automobile Industry Academia Government Collaborative Project. Yeah, and also we work as a major player for Hiroshima Research Complex. Then our target achievement is we organize the international symposium every year. And so this year, 2020, the date is tentatively December 7 to 9 in Hiroshima. So please make a plan from BITS-Pilani to attend this symposium. Also, we organize the international workshop, seminar for public, not yet decided the date, but we are now planning. Also, we publish the papers or textbooks, whatever. Also, our goal, we educate, we output the PhD graduate 20 per year, foreign student 20 per year, and technical papers 6 per year. Well, this kind of target. Based on the last 4 years HUACE achievement, the university recognized ACE as an independent research center. So now HUACE is not the promising research initiatives. We are now, HUACE is now the independent research center in University of Hiroshima University. Okay, so ACE research group. So energy use combustion group, secondary energy conversion, hydrogen or biofuel group, primary energy production, nuclear fusion group work together for getting the this kind of very kind of challenging target for efficiency improvement or next generation, next societies energy source production. So let's take a look at the each group research very quickly. So energy use combustion IC engines. Actually, this is my area, Nishida here, and Professor Ogata, Professor Luo. He is one of the speakers in this workshop, working on this brand combustion. And we had the joint research with Mazda Motor Corporation. Then Mazda developed, and Mazda and our group jointly developed the new diesel engine combustion system, which reduced emissions very much, and also improve the thermal efficiency. So smart spray engine combustion is our research target. Professor Miyoshi is combustion chemistry guy, so he is now working on the next generation fuel. What is the next generation fuel? From the viewpoint of renewable or continuous supply. So current innovation of fuel and combustion. Professor Takuma Endo. Professor Endo is working on the laser-induced spark for lean burn combustion. So laser ignition for super lean burn engine is really critical technology to enable this super lean burn engine. Professor Shimokuri, he's a combustion engineering, working for the microscale next generation combustion. Now let's move to the secondary energy conversion biofuel. Professor Nakashimada, he's working on the biofuel. His project is from the seaweed to the new energy and the new material. And this is the table, how we have the biomass of marine algae. So we have the very much marine algae. So Professor Nakashimada working on fuel and the materials from marine biomass. Professor Matsumura is one of the speakers today, working on the supercritical water gasification hydrothermal reactions. So gas and liquid and solid fuels from biomass is his Professor Matsumura's research. And hydrogen. Hydrogen is studied by Professor Ichikawa. Hydrogen storage, ammonia absorption materials, even lithium-ion battery is his research area. So his research is toward the hydrogen society. Professor Kim is a combustion guy, and he's working on the hydrogen combustion and the hydrogen combustion safety. So storage, utilization, safety, technology of hydrogen combustion. Primary energy production, nuclear fusion is research is made by Professor Jozaki, nuclear fusion. Okay. Then there is a fusion as a next generation energy source, long-term research. Now, maybe this is the last part of my talk. Let me introduce our ACE Professors Research Collaborative Research. This is supported by Ministry of the Environment, Japan. Started this year and a 3-year project. And the research title is Systems Development of Highly Efficient Hydrogen Withdrawal from Stock Farming Waste with Electrolysis Technology. This is one of the part of the research, and another part research is electric power generation using withdrawal hydrogen assisted clean-burn methane gas engine. So I don't know if you know about this kind of thing very well. We have the what this is. Yeah, we have the farm in the country, and the cow, pig, or hen drop this waste increment. Yeah, and increment emit sometimes, or very often, ammonia. And ammonia is diffused into air or sewage. Then it is very smell, and the tree withered, and water pollution happen. It is not good. Then animals, Mr. Cow, get sick. So this is the current situation. In this project, we use the thermal water pre-treatment by Professor Matsumura, methane fermentation by Professor Nakashimada. We make CH4, methane, from this waste. But there's a byproduct, ammonia. Okay? By using electrolysis technology, Professor Ichikawa, we decompose this ammonia into N2 and hydrogen. Then this hydrogen is used with methane for clean burn gas engine power generation. And this research is made by Professor Kim and by myself, Nishida. Then this electric power supplied to the cow shed and air-conditioned cow shed. Then Mr. Cow get healthy and make high-quality milk. So environment-friendly system development. Okay, this is the last slide. So in summary, HUACE, Hiroshima University ACE, Advanced Cooperative Energetic, focus on the energy consumption research, combustion, IC engine technology, energy conversion research, biofuel production, heat production and storage, and energy creation, nuclear fusion and artificial solar energy. So this photograph back is the, we have the Sake festival once a year in October, October. So I don't know Mr. Goel during this festival, but this is a really interesting festival. So next time, please make a plan. Yeah, sizable sake capture. Thank you very much for your attention. I'm happy to take some questions from the audience.
Thank you very much, Professor Nishida. I would like to clearly ask participants to ask questions if they have. They can just type on the chat box.
Let's go ahead.
I think if not, we can move on. Thank you very much, Professor Nishida. I think a lot.
Thank you very much.
A lot of things which we can possibly do together, and I think we should explore that. We should leverage that opportunity. But we will discuss further after completing all the presentations. Moving on, I request Professor Banasri from BITS-Pilani campus to start presenting. I request her to, if possible, limit to 15 minutes.
Good morning, everybody. Am I audible?
Yes, we can. Please carry on.
Okay. First, I would like to thank both the University and BITS-Pilani workshop. Thank you for
Professor Roy, I think your voice is a little echoing, actually. Can you please check on the technology if possible?
Okay. Yeah, it is. Can you hear me?
I think please carry on. We'll see how it works.
Okay. So let me start the video. So myself, Dr. Nishida, I'm part of Chemical Engineering Department of BITS-Pilani campus. So today I will talk about agricultural residue as research material for the conversion of agricultural residue to renewable energy source. So in this project, I am working with Professor Yukihiko in University. Our joint student Satish is also here. So the idea is that conversion of agricultural residue, because there is a very general audience, I try to keep it very general. So my talk will be into parts. So agricultural residue most of the resource. So let's look what is the worldwide and Indian scenario in terms of agricultural residue. So here is, we can see the worldwide data for production and energy potential so 2003 and 2030. Okay? So as you can look here, we can see that 2013 the worldwide bioresidue production was 3.8 gigaton, whereas it increased to 32% in 2030. Okay. Now, if I look at the energy, agricultural crop and residual agricultural residue situation in India. So there is only very recent data based on the Punjab. We are focusing on the surplus biomass and energy production potential from this biomass. So now the biomass is surplus biomass is very different from the gross biomass generation. So what happened? The 75% of these agricultural residue are used for domestic and for commercial activities. So among these commercial activities means mostly bioenergy, biogas, methane production, pulp industry, packaging material, and in domestic application using the transporting animal fodder, compost, manure, hatching, mulching material, this kind of industry. So out of this, 75% goes to this kind of application. And what is extra? That is 25% of the gross biomass generation. That is your surplus biomass. And if you look at total potential energy generation can come from here 1.7 gigawatt per year. Now, the India produced more than 600 million tons of biomass per year, and at present, the MMNE potential is 18 gigawatts of energy from the biomass, whereas it is only 30% of the potential is being harvested at this current situation. So now, if I look at the crop production, crop residue generate and burn. So what happened to this surplus biomass at current situation? The people generally burn it. So if I look at the statistics, then residue generated and residue burned, two states we are considering here, Punjab and Haryana, 2017-18 data, which shows us that in Punjab residue burned is 20 gigatons, more than 20 kilotons, and in Haryana it is more than 9 gigatons, right? So this burning actually has that effect. So before doing that, I would like to mention another thing, that if you look at the crop production and the residue generation, residue burning, the nature of residue generation and residue burning, that is also varies from state to state, area to area in India. So like if I consider Punjab and Haryana, in Punjab, the rice 41% production, residue generation, and out of that 70% is burned. Whereas in wheat, it's 53% residue generation, but most of this is used as a animal product. So there is a variation in terms of nature of the residue production. Similar thing we can see in Haryana, 64% wheat straw, wheat residue production, 40% is burning, whereas 26% production of rice related agricultural residue, but more than 50% is burned. So now, when you're looking at this burning, how this burning is affected. So here is the worldwide global scenario 2016 data. It shows that all countries, they have agricultural excess residue which they burn. Like in United States, the total CO2 emission due to this burning is 3.73. But if you focus in our India, you can see that our case, the major crop agricultural residue burning is coming from the rice. Corn, wheat, and little bit sugarcane also involved. We all know that most of it is the Banasri, which is coming from sugarcane. The sugarcane factories, which is converting sugarcane to sugar, they use this Banasri for heating purpose. But still, there is metric ton per year, 3.2 metric ton per year. That is not very small amount that is being burned. So total CO2 emission we are getting here 4.25 metric ton per year. So now these CO2 and other pollutants will see that affect our environment and affect health. Not only that, it affects our soil health also. Wherever the burning is happening, because you have to keep in mind that is buying these farmers, they do this locally, and that also bad for the soil. It lost nutrients and other beneficial microbes in the soil. So now, if we look little closer, that there is emission of various pollutants from burning of the different crops residue in Punjab year 2017-18. So this is different districts of the Punjab state. So we can see that number of pollutants like particulate matter less than 2.5 micron, paint, sulfur dioxide, CO2, CO, NOx, ammonia, methane. So the amount is very huge, right? Say particular matter 2.5. It is coming out close to giga kg, right? So same thing if you look at in Korea, same year 2017, 18, using was data, and what it is showing us the amount of pollutant coming out from driving these agricultural residue is huge. So here interest of using this agricultural residue, one is to convert the surplus residue to meaningful, like renewable energy products or other chemicals. That is one interest. Another interest is to avoid agricultural environmental pollution, right? So from this point of view, we started this project. And here in part 2, I will talk little bit, again very general way, that how to use agricultural residue to convert to the carbonaceous material and that renewable energy sources. Because we have to keep in mind that agricultural residue has multi potential. We can convert it to renewable energy source, and when we are looking to converting agricultural residue to renewable energy source, then what will be the criteria? So most important criteria is the composition of the cellulose. And because so far this is the easiest composition, this is part of the cellulose biomass to convert. So for example, rice or wheat, right, or say sugarcane, the cellulose percentage is much higher than some other like mustard. So so this is one important factor we use for converting to renewable energy sources. Or when we going for the catalyst conversion. So for catalyst conversion, we use because it is carbon will be less only, other ingredients supposed to burn up, right? So like here, if you look at the sunflower straw, as a peach tree, very high carbon content. So this is one criteria we generally look at. So now, when we look for how to convert the agricultural residue to catalyst, so here I mostly take the example of the activity plant. So if we are taking the biomass waste, it can be converted with activation or without activation. So with activation, we can try chemical, we can try physical. Both cases, we can try the hydrothermal carbonization. So this is one area where I would like to also work with Professor Matsumura. And then other methods also use like templated. The purpose of the templated is controlling volume and the pore size distribution. Okay? Because when we are looking to use them as a catalyst, a certain pore size distribution is essential. So this method, as you can see here, so we start with biomass, we go for physical or chemical activation, and technically the chemical activation is supposed to give you higher surface area, better porosity. So people right now is more interested in chemical activation, but again for physical activation you can avoid the pollution. So that is the thing. So then you go through this chemical or physical activation, and then ultimately you reach the carbon. So that question comes, Okay, in that carbon the property. The property is essential if you want to consider as a catalyst. So where is some carbon material like say activity carbon right now and graphene oxide that we are discussing. So here the surface area is 1,000 right? Pore volume is 2 per gram and cost wise also low. So that is economical as a catalyst. So now if you compare it with the templated porous carbon, so that is what we see. The costing pore volume may not be that high, surface area is fine, but cost wise is high. So one of the interesting is that to directly convert a simple method with good and good property day. So that is the focus of our work here. So now when you are getting the basic carbon, basic catalyst, next will be the modification, right? So now there are different modification as you can see. So one case is a thermal process, directly take it and heat it, and then you are doing physical modification or you are doing the chemical modification. Now chemical modification can be done by using chloride, like zinc chloride modification, or it can be done by using some BITS, like KOH, NOH. Or another method is to add functional group to the surface. So you fix it the biomass after pre-treatment, and after that you can use sulfuric acid for acid modification. So if you use the acid modification, then you are practically attaching certain functional group on the surface of the carbon, right? Or you can add metal nanoparticles like here iron, nickel, titanium, or you can use some graphene oxide or nitrogen, sulfur, phosphorus coating. So now what is the purpose of this kind of different kind of functionality attachment of surface modification or that kind of physical or chemical modification? So the purpose is application. So if you look at a very simple contact picture, which is showing different types of carbonaceous material, they have different way of modified and different types of application. For example, photocatalytic, right? So you are taking your carbon material modified with titanium, things like that, and that modification creates these oxyhydrogen oxygen particles, and that can help you to remove the excellent organic chemicals. So,
Professor Rai, can you please conclude now? Thank you.
Yes. So right now we are interested for the hydrolysis and esterification and transesterification because these are the direct mechanism, a direct method you can say to convert like cellulose to BDC sugar or full fatty acid to diesel like that. Okay? So because here we are in hurry, so let's talk really quickly. So how carbonaceous catalysts improve the conversion of the triglyceride to the biodiesel. So what is happening here? The carbon surface is the hydrophobic surface, but that hydrophobic surface automatically rejects the production like water or hydrophilic glycerol, and that helps for the simultaneous esterification and trans-esterification reaction. So by esterification, what you can do here, we are seeing that as acid catalytic esterification mechanism, where acetic acid just means the triglyceride is nothing but one chain acid. Okay, there is a one acid group attached at the end. So the sulfuric acid taking this oxygen lone pair, right, and transferring this proton to the acetic acid, and then it goes from intermediate ion and then ethanol is coming in the picture. The lone pair of oxygen is attaching with this carbonyl ion and was transferring specific charge rearrangement of the structure is happening, and so this rearrangement of the structure, transfer of the proton, that eventually leads to the formation of the effect. Okay. So this is a simple way of showing how calculation patterns work for the disease. Similarly, we can look how calculation patterns work for the agricultural acidity sugar. So like here cellulose. Cellulose is nothing but a. So now here three groups generally attached here: OH, COOH, and Sanket. Now when OH and COOH they have some synergistic influence, they attach within cellulose group to hydrogen bonding, and then actual sulfate group that acts as a catalyst and have the hydrogen. So this way the total activation events can decrease and it can increase the total conversion. So if we look at how the agricultural residue can be helpful, here is the concept. So from cellulose amplified cellulose to depolymerization, it is converted to plus sugar, a form of sugar that could be glucose, that could be glucose, and by the use of either leucine or phosphoric acid, it can be break or converted to different valuable chemicals. So when these chemicals all used, it is helpful for the human society and human civilization. So I would like to conclude here. Thank you very much for your attention. Any questions?
Thank you very much, Professor Roy. I again would like to request the participants to please write their questions in the chat. We'll address them subsequently. Now, thank you very much, Professor Roy, once again. Now, I would like to request Professor Yukihiko Matsumura from Hiroshima University. We are looking forward to hear him on biomass treatment using hydrothermal conditions. Professor Yukihiko Matsumura, thank you.
Okay, can you hear me? No, of course.
Srikanth,
can you hear me? I'm confused. Am I muted?
You are visible.
Okay, so you can hear me. And okay, thank you so much for Sanket. And I would like to first present the video of our center, which is this one. And after that, I will talk about my research. Okay, thank you.
Thank you very much, Professor Matsumura.
This is what Professor Nishida already explained, but I hope that this game helps you to understand our activity. Okay, now I would like to move to my presentation, but for this purpose, I have to move a little bit thing. So I go, where should it go? Yeah, the PowerPoint. Okay. So Sanket, can you see my slide?
Yes, we can. Please. Yes.
Thank you. So please let me explain a little bit about my own research, which is the biomass treatment using hard summer conditions. Well, as Banasri has already explained, we have a lot of biomass, waste, annual produced, dry, wet, and others. When we're talking about biomass conversion or utilization, what is important is the moisture content of biomass. When biomass is dry, you can burn it. But when biomass is wet, it is difficult to convert it efficiently. For example, food manure, food sludge, food waste, water hyacinths, and algae. These kind of things can't be burned or can't be heated because when you apply heat, water evaporation takes place and biomass does not react. So what we are working on is the hydrothermal technology. Maybe you know the water phase diagram. When temperature is low, water is ice. When it is heated, it becomes water and then steam. But when the pressure is high, the water can be liquid phase even at high temperature. And when the pressure is above 22.1 megapascal, water can be in supercritical situation where water is actually very, very reactive. So using this reactivity of high temperature, high pressure water, we can convert biomass very effectively. For example, when you're talking about pretreatment, we can do hydrothermal pretreatment. When you're talking about conversion, we can produce gas or liquid or solid. The gas production is called supercritical water gasification. Liquid produced by direct liquefaction, and solid is produced by hydrothermal carbonization or the slurry field production. When you're talking about the material utilization, hydrothermal conditions can be used to separate biomass components, cellulose, hemicellulose, and lignin. So when you map it with the temperature reaction time, you can get something like this. When temperature is high, you can rapidly convert biomass into gases or fuel gases. And when temperature is mild, you need a little bit more time, but you can get liquid fuel. Further, when temperature is low, you need long time, but you can get charge, hydrocharge, which can be used as solid fuel. Other applications are also available, like hydrothermal pretreatment, which is the treatment of biomass in hot compressed water, so that components can be separated, but also reactivity of the biomass is improved. So, for example, when you're talking about methane fermentation, hydrothermal pretreatment assists the high-speed methane fermentation. In our laboratory, we are working on this technology, and here's one example. This is about supercritical water gasification, where biomass is converted to fuel gas in the supercritical water, which is hot compressed water. The reactor is something like this. You can put the biomass slurry, or which is pulverized with biomass, in this piston pump, and you feed water under high pressure from the other side of the piston so that the biomass can be pushed out of the pump, sent to the press heater, and then treated in the reactor. Here, the gasification takes place. The gasified biomass is cooled down, depressurized, and then the produced gas is spontaneously removed from the liquid phase so that you can get clean gas without tar. We could change the concentration or the amount of catalyst or reaction time or temperature to find out the reaction characteristics, and then could find out the equation of reaction like this. In parameters, we have two parameters, which is KAC and K10, could be determined something like this. As you can see, free exponential factor and acceleration energy are determined for these two reaction rate constants. So, in this way, we are doing the analysis of hydrothermal treatment of biomass. Of course, this kind of technology can be applied for the carbonization, liquefaction, or others. Also, if you have some biomass that is to be treated hydrothermally, we can be agreed, idea to collaborate, agree. So, I would like to thank you for your attention, and this is difficult, but Daniel and Sukuna. Thank you.
Thank you very much, Professor Matsumura. Really, my pleasure to hear you. I think we should be able to explore some of the topics where we can work together in future. I'm really looking forward to work with you as well. Thank you so very much. Thanks a lot. I think now we'll have Professor Arshad Javed from BITS-Pilani. We'll be talking on microfluidic system for combustion gas sensing.
Yeah. So let us. I hope you can see the slides as well as you can hear me.
Yes. Yes.
So good morning, everyone. I'm Arshad Javed. I'm going to discuss about the microfluidic sensors which can be used to sense liquid as well as gases. I think my video is not on, isn't it? So let me go back and start my video. Yeah. So I'm going to discuss about the microfluidic fuel cells which can be used for gas as well as liquid sensing of different compositions. When you talk about sensing, it is actually, and especially gas and liquid sensing, it is actually very, very important activity in the industrial as well as service environment. Where we wanted to know the environment condition, we wanted to know the condition of object, for example, spoiled food, or even in the biomass example, you can know what is the chemical composition, what are the gases coming out, and whether it's useful to be treated or not, correct? So it's a kind of, we can say, kind of knowing the condition of the object. Then we will be able to know the chemical compound, chemical quantity, what is the percentage of any liquid component or gas component in the sample. So conventionally, specialized methods such as mass spectrometry and gas chromatography is available to do this task, and these are very pretty accurate methodologies. However, these are large in size, okay, and requires skill to operate. You require some skilled labor, skilled people who can operate this, and then you can know what are the different quantities of the gases and the liquid chemical compositions, and the cost is also high, and it's quite sophisticated equipment, so cannot be used for different applications. And the challenges in such methods are their resolution, the kind of resolution you look for, sensitivity, how quick you are able to provide the solution or the value of the chemical compound, their portability or compatibility to be used at the remote places or the kind of like different chambers or pistons or different kind of flow system where you would like to know what are the typical compositions, and then the power requirement. So these are the key challenges which are faces when you go for different kind of versatile application. So we would like to propose here a kind of self-generating system. Self-generating means it generates its own energy to sense the liquid composition or the gas composition, and it does not require external power source as in the previous one, and it is compact in size and low cost, and mostly it is use and throw type of thing, which can be supplied at the point of application and then can be discarded after the application. Their sensitivity and resolution is an issue on which we would like to focus. And when you summarize these all things, we find out that fuel cells and especially micro fuel cells can be used for these kind of sensing applications. So in our laboratory, we have developed multiple types of fuel cells as discussed by Professor Goel. And then we look forward these fuel cells to work as a liquid or gaseous sensor. So first of all, I would like to introduce our research team in the fuel cell area. Mr. Lanka Tata Rao and Mr. Prakash is active researcher in this area, along with Dr. Satish Kumar Dubey, myself, and Professor Sanket. So this is the research team which works towards the fuel cell. Let us come to the technical presentation and what are we having to present here. So I would like to present the state of art we had in the area of fuel cell, that is paper and pencil based fuel cells. Then how we have developed a functional relationship between the input parameters and the output of the fuel cell. Then how to standardize the electrode, their sensitivity. And then we further increase the sensitivity of these electrodes, and that is how we will be able to increase the resolution of the sensor if we make in that way. And finally, we have some initial data of sensing oxygen as well as hydrogen. So let us start with paper and pencil kind of fuel cell, where you can see cellulose paper is used to have capillary action. And with this capillary action, we'll be able to react sulfuric acid with formic acid. And the reaction happens within the boundaries of colaminar flow, where only proton can move from one side to other side. And there are two electrodes, you can see here, gray electrodes. These are made using scribbling pencils, the common pencils on this cellulose paper. So these pencils, when these pencils are scribbled over this paper, it creates air breathing electrode which can take oxygen from the atmosphere and it can react with formic acid, and then electrons are being emitted, electron, proton as well as water molecules in carbon dioxide. These are coming out from as a reaction part, and then the electron travel through cathode in this reaction. And absorbent pad is used here to enable flow towards left to right direction. And this has also got an importance, and we have also studied the role of absorbent pad and their particular size to have maximum output from this cell. So after establishing this experimental setup, we have first of all observed what is the electrode gap, the gap between the electrode. Here you can see the electrode. And this white line is the bare paper through which the fluids are flowing, that is electrolyte and fuel. And then we have tried to observe what should be the gap of this between these electrodes so that we get maximum power from the cell. This maximum power serves as a resolution value and sensitivity value when we use it as a sensor. And it basically can sense the fuel concentration, electrolyte concentration, and environmental condition. That refers to sensing of gases, whether it's oxygen or different kind of gases, and then we can characterize and use it as a sensor. So here we have different type of gaps which we have introduced in our experimental setup. That is 1 mm, 2 mm, and 3 mm. For example, that these are the values we have taken, and we observed that corresponding to 1 mm, we get better performance. It is stabilized. Though the values are not very high, the values are high for 2 mm initially, then it goes down. But when you see for the performance along 1 mm gap, you'll find that it is more stabilized, on the course of time, and it runs up to 600 minutes. And then here is the polarization curve, figure 1.3, where you can see when we create a gap of 1 mm, we get highest power density around 260 microwatt per centimeter square, and the current density is also quite high for this kind of gap. When the gap is further increased, the current of power density is decreased. So this is what we have kind of optimized value between the electrode gap. Then we try to observe that what would happen if we change a different type of paper. So paper is going to play a major role. It actually decides the porosity, the oxygen business of the shell, and the exchange of electrons from one side to other side. So there are various phenomena, including the environmental factor and noise factor also, which is going to be affect the paper. So we have taken different type of grades of paper on that cellulose paper on which the whole platform is being constructed. So we have taken different grades, and we found that a particular grade, that is grade 1, is going to be best one, and it gives the highest amount of power density and current density. And other grade of papers are not performing well. We have done in-depth SEM analysis and UDS analysis to see what is the actual reason and why it is behaving in different way. So we observed that the basic porosity and kind of a structure which is provided by the paper threads inside is going to be responsible for this observation. Then once we have developed the what you call the initial setup of fuel cell, we try to develop a mathematical relation between the input and output parameters. The input parameters, as you can see in this table, are various, including the environmental factors. It starts from geometrical factors, like it also, the output is power density, current density, and open voltage. So with respect to these three output, we try to map what are the different input that can be related to these output, and that is going to develop a relationship between the quantity which we would like to sense and the output, and that is how the characteristic of the sensor can be defined. So it starts with geometrical condition, the shape and the size of the paper, cellulose paper on which the whole cell is formed, the electrode gap as we have seen earlier, fuel, type of fuel and their concentration, type of electrolyte and their concentration, then different type of pencils we have used, and we have used HB, 2B and 6B pencil and different other types also to observe in which condition we get the maximum output. And these are going to define the graphite content and the kind of flakes which are formed on the paper. So it affects the physical characteristic as well as the electrical characteristic also, where the resistance of the anode and cathode can also be varied through these grades of pencil. Then when we make the electrode, we need to scratch by hand on the edge of this paper, and that is how these black lines on this photograph are shown as an electrode. So these are handmade, where a person sits and scratch or scribble the paper 80 times, 60 times or 40 times on the cellulose paper, and that is how I try to see what is the effect of these number of strokes on the paper. Then the next parameter was fuel and electrolyte concentration, which was 1:1, 1:2, and 1:3.75. And cell material was taken as constant. That was Wortmann filter paper with grade 1, which we have observed in the previous experiment, that it suits better to the cell. Then different combinations of these pencils are used: HB, anode cathode, then HB2H, HB2B, and HB6B. When we go for hardest size, the resistance changes, electrical resistances, and we go for 6B, the graphite content increases, and the resistance change accordingly. One more thing used to happen, that when you take very soft pencil, the graphite scales form very uniformly on the paper, and it affects the oxygen leading property. So that is also going to be affected. It means that it is not a unidirectional data, but it's a bidirectional, where we see a maxima at some point and minimum at some point. So there is a need of optimization and mathematical relationship in this particular phenomenon. And then also we have tried to observe different kind of orientation, vertical and horizontal, which is going to be affecting the colaminar flow, which is tried to be established in this particular setup. And the colaminar flow acts as a membrane which permits only proton to move from one side to other side, from from electrolyte to from fuel to electrolyte, and then electrons are bound to move throughout the outer circuit, which generates the electricity, and that is how the sensing can be performed, and you get a response from the sensor. Then what we have done, since this particular phenomena of fuel cell involve a lot of input factors as well as a lot of environmental factors. That is why exact mathematical modeling of this electrophysical, or we can say electrochemical physical system, is very, very complicated. So we have taken help of the statistical tools where you can define the input factors which are controllable. Controllable means you have your own control over the number of strokes, electrolytes, and setup condition. But at the same time, we don't have control over the atmospheric condition. You can say the slight variation in geometry, errors, and human error which is involved in the stroke. So a lot of environmental factors are also considered in this way, which was not possible if we would have done through, we would have done with the what you call the mathematical way. So you can see that we have observed these different type of combinations, and we found the best performing scenarios also, and that is what we try to focus here. So in this table, you can see we have defined multiple experiments. We put the setup in horizontal as well as vertical, and then different fuel concentration as discussed previously was used, 1:1, 1:2, and 1:3.75, and different strokes of the pencils were used to develop the electrode. And at the same time, for each combination, different combination of pencils are used to develop the anode and cathode. And then we found that this particular combination in horizontal 1:3.75, 40 strokes, HBM6B gives the best result in terms of current density and power density. At the same time, when we put it in vertical, we found that the same 40 stroke performs better with the same HBM6B combination for anode and cathode, and a power density and current density highest in this configuration is observed, though its value is lower. So one of the observation is when it is horizontal, we get more power and current density compared to the vertical scenario. Then HBM6B is the best combination because there is a lot of difference between electrical conductivity in HB pencil and 6B. Then we observed the stroke is when it is less 40, it is better because it allows a self-breathing property to the electrode. While when you go for higher number of strokes, the electrical property improves, but the physical property on the paper, the microstructure, gets disturbed to have a good oxygen breathing property. We developed the mathematical relations. Those are multiple line relations. So I thought not to present and to present their performance. We have developed the mathematical relations, and then we try to check how it performs. So you can see here a graph between actual and predicted value. Actual values are taken from the experiment, and predicted values are taken out from the mathematical relations which are developed. And there the output response was taken as OCV, output current, output voltage value, and then current density and power density. And input parameters, as we have seen, setup direction, fuel concentration, and strokes were taken as the controllable factors. And we observed, these are two results only shown out of multiple results, that this performance gives you almost very good equation where you actually get exact same value giving two conditions. It gives best value between the actual and predicted. And here you can see the worst one which we observed is also very fine. It can be used for sensing tasks, where you can see that the actual versus predicted actually matches very well to each other. And then we come to the desirability. Desirability means we have different objective functions. Different objective functions means we have current density, power density, and output current, output circuit voltage. So here we observed, as we have seen earlier, we would like to manage the best among the three. So in best among three, we found whatever we found earlier. With the same statistical analysis, we observed that HB and 6B performs better, and you can see the desirability somewhere around close to 0.9, means 0.9% or 90% we are very much satisfying all the three parameters, and the same factors are coming out as the output of this statistical analysis, which actually confirms the experimental analysis also. Then in that setup, we are now at the third stage of our presentation. where we have focused, and you might have noticed that we have a manual process of scratching the pencil over the paper and try to develop the electrode. That was not a very standard method. So we tried to standardize this process by developing an automated system. And the video of this particular device has been shown by Professor Goel's presentation, where you saw a plotter and it was trying to make an electrode over the cellulose paper. So there we try to standardize and make a uniform pressure in all spokes, so that when you produce an electrode for multiple applications, you get actually standard values for the output. So in that way we try to standardize, and we have used an indigenously developed automated system where we use the force sensor, we use the spring to apply the force, and there is a mechanical arrangement to change this force. And we have also observed the different force values for different strokes. So you can see that it almost remains constant between 2.1 to 2.2 range, Newton range, and does not vary even if you go for multiple number of strokes starting from 30 to even 300 strokes, the force value does not change. The spring applies a constant pressure, and the pencil also rubbed out, even though we found that from 30 to 300, within this range it is almost constant from 2.1 to 2.2 newtons, and that is how we get a uniform scaling of graphite on the cellulose paper. So after that, we try to scientifically check it using EDX analysis whether we actually get the uniform quality or not. So we try to see the chemical compositions coming out from EDX analysis corresponding to automated as well as manual pencil stroke. And we found that the standard deviation and standard errors are quite lesser in the case of automated pencil stroke compared to when we do it using manual. So we have taken multiple samples and we try to found the data for standard deviation as well as error. At the same time, the Carver percentage for the same number of stroke is found higher in the case of automated compared to the manual. It means, and it is obvious, that automated or uniform or standardized method to develop electrodes are quite better than the manual pencil strokes. So that was another study where we tried to standardize the electrode, and then we ran a simple experiment and tried to see where the maxima of this current and power density comes. Later, we thought, why not to change the electrode itself to increase the sensitivity and resolution of the cell as a sensor. So there was a material called as laser-induced graphene, and this was very attractive to us because of its flexibility in manufacturing and easiness of developing the device. So this particular methodology is used to develop the electrode. We have taken a polyimide sheet over which CO2 laser system is used to develop the electrodes, as you can see here through black lines. And then we develop a sandwich structure in which across two acrylic sheets we have electrode as well as PDMS channel. Okay, and in this channel the fuel is an electrolyte is flowing, maintaining a colaminar flow, and one side of this channel is covered by this sheet which serves as a function of electrode. So we can see that the construction is easier, and here you can see the channel wells through which the electrolyte and fuel can communicate through the cell. So this is the physical setup, and these are the parameters. Electrolyte and fuels are same. So electrodes are LIG electrodes have higher output. Fuel is formic acid, electrolyte is same as before. Catalyst we have to enhance the performance of this electrode, because as you know in the previous slide there must be a lot of different electrical property from anode to cathode.
Dr. Javed, can you please conclude if possible? Thank you.
Yeah. So that is how we try to enhance, and we have seen surface observation, and we found that AG ink performs better compared to any other catalyst. And then this is the important thing where we try to see the effect of catalyst, and we found a large difference. And then the presence of oxygen is also sensed here as a preliminary result. We observe there is a big gap, and that can serve as a higher value of resolution when it is used as a sensor. Now, I would like to come to the last topic where we try to sense hydrogen through this particular sensor or use this as a fuel. So it is used as a fuel and H2SO4 plus H2O2 is used as oxygen plus electron. And here also we can see that there is a good resolution obtained, like difference in output when we use different concentration of hydrogen. So this gives an idea that particular, so though it is very large, 20 millimolar, but even though since you can see the output is in millivolt, so even if you go for nanomolar, we may get quite better value to be sensed. So with this, I close my presentation. And the conclusion here is that fuel cells are promising methods which can be sensed, which can be used for sensing different chemical compounds, and it can be used for dissolved gases and liquid also. And the atmosphere we refer to from gases which are mixture of gases, so we sense for this work. It is, as we have seen, easy, less costly and affordable, and it's miniaturized and suitable for remote applications. So with this, I will close my presentation. Thank you. If you have any questions, please chat. Thank you very much.
Thank you very much, Professor Javed. Yeah, again, participants are feel free to make questions. Meanwhile, I request Professor Luo Hongliang from Hiroshima University to present on droplets behaviors of impinging spray by gasoline hole type injector. Professor Hongliang.
Hello, can you hear me?
Yes, we can hear you.
Okay. Thank you very much. Thank you very much to invite me attend this workshop. Good afternoon, everyone. I would like to introduce the recent work of my research. So the title of my presentation, as shown, is the droplet behavior of impinging spray by a gasoline hole tap injector. My name is Hongliang Luo. The family name is Luo. Firstly, I would like to introduce myself. My name is Hongliang Luo, assistant professor in Hiroshima University, and this is my homepage. I'm focused on the fuel spray impingement and fuel droplet behavior, combustion, and published more than 30 articles, and also some reviewer of the international journals such as the Applied Energy, Fuel Energies, and so on, and also the membership of the Japan Society of the Mechanical Engineer, the Japan Society of the Automotive Engineer, and the International Society of the Automotive Engineers. This is the contents of my presentation. Firstly, I would like to show the background and objective. Okay. So as we know, it is difficult to avoid the impingement of the liquid fuel on the piston head and the cylinder wall. The field on the adhesion may increase the particulate matters and burden hydrocarbon and insufficient combustion. So generally, the droplet behaviors reveals the quality of the spray and the atomization, which can determine the subsequent impingement and the fuel film formation. Therefore, the macroscopic droplet behaviors is very important. However, for the previous works, not only for the free spray but also for the impinging sprays, only owing to the dense particle only at the periphery regions or the far region from the wall can be characteristic. For our previous works, we have already observed the droplet behavior before impingement and after impingement. However, we can see, so for these figures, we can see at the X of the sprays, it is dense regions, so it is difficult to recognize the droplets, not less to analyze the behaviors of the droplets or ligaments. So the objective of this work is to this work is to analyze the impinging sprays in the dense region along the spray X under the engine-like conditions. In this studies, the spray slicer is used, and the jobless behaviors of the slicer spray is reported through the PIA method. So the second part is the experimental setup and the method. So this is the experimental setup for our research. We call it the PIA. The full name is the particle imaging analyze. We can see double pulse lasers illuminate the sprays, and the CCD cameras can observe the spray. So the maximum resolution for this equipment is 0.8 micrometer per pixel. So we can see the resolution is pretty high for observe the droplets. Next is the image processing. So this is the raw image we got. And then we reverse the colors to get the better recognition. Then using some of the refined criteria such as the threshold value, the roundness, the pixel numbers, area diameter, so we can filter the droplets what we want. So we can see in this part we can get the droplets diameter from 4 micrometer to 100 micrometer. So the very tiny droplets we can get and characterize their behaviors. And this part is for the droplet diameter and for the droplet velocity. So we can see this is the time chart for the trigger signal in this equipment. So for the each triggers, we can get from the CCD camera, we can get two image with the internal timing of 0.4 microsecond. Then with this very short timings, we can calculate each droplet velocity like this. So then we can get the droplet velocity, droplet diameter. Then we can observe the droplets and get the droplet characteristic very clearly. Next part is results and discussion. So this is the design for the slicer. So we can see this is the specification of the injector, slicer, and spray. You can see after the slicer is the cone structure with the two slices, and the distance between the slicer we can change. We can justify the distance from 0.4 micromillimeters to 0.8 millimeters, or even very smaller to 0.04 millimeter. Then after slice the spray, so we can see the spray become very slim, and then using the lasers and CCD camera, we can observe the droplets very clearly. Next one, we just show some image. So we just slide some typical locations that, such as just go through the slicer, just impinging the spray, just impinging on the wall, just the splash of the wall. So we can see the droplets. Very clearly. Of course, this part is only at the spray tip, so we can see the droplets very clearly. Well, so we change like I introduced, we can change the distance between the slicers. So the result is 0.2 millimeter, 0.8 millimeter, 0.4 millimeter, and 0.8 millimeters. So increase the distance, we can see more droplets will pass through the slicer, and the dense region become the image become very dense, and it is difficult to observe the droplets. Well, at 0.4 millimeters, we can even observe the splashed crawl in this image. So increase the distance, the clarity decreased. Well, then we want to check the velocity. So this is the velocity at different locations and different thickness. So we can see the results show that when the thickness is 0.4 and 0.8 millimeters, there is almost no difference between them. While decrease the thickness to 0.2 millimeters, the velocity decreases sharply, which suggests that little effect on the velocity decreasing when the thickness is larger than 0.4 millimeters. Of course, this part is our previous work for at the spray tip. Well, for the real sprays at the quite steady, as we show in this part, this is the quite steady state. So for the quite steady state, it's more important to predict the multiple droplets behaviors than the initial state. So this part is the initial stage, just as I showed is as the spray tip. Then therefore we want to analyze the droplet behavior as the quite steady state. Then I show. So for the 400 micrometer means 0.4 millimeter for the thickness. We can only observe the droplet behavior at the spray tip. While decreased to 100 micrometer, we can see the spray tip droplets at the spray tip more clearly. While decreased more, while changed to as a quite steady state, it is difficult to observe. Then we decrease to 0 to 40 micrometer, means 0.004 millimeter. Then at this very short, very narrow distance, using the spray slicer, we can see the droplet behaviors very clearly. And the injection pressure is 30 megapascal, ambient pressure 0.1 megapascal. Then one thing should be noted that when the distance at 40 micrometers, it cannot say this is a real spray. Actually, it is just multiple droplets impinging on the wall. Then we analyze the droplet behavior under these conditions. First, I show the morphologies of the droplet behaviors at different locations as we show in this part. So the horizontal axis is the x, and the vertical axis is the y. Different locations are shown at 50, 70, 20, 22. It means the horizontal axis from the original. Then results at different injection pressure, which are shown like in this part. Well, at these locations, we can see that means 20. So when at the 20 locations, some large droplets can be seen. That means the secondary droplets with the large size may be one possible explanation for that. Then we want to analyze in this part more and more to get the mechanism for it. As I explained before, in using the PIA, we can not only get the diameter but also get the velocity. So this part we show the diameter and the velocity distribution of the droplets and the different locations and the different injection pressures. So we can see with the jet direction, with the jet's development from 50s to 22s, the velocity decreased sharply, while the diameter distribution almost no change. So the impingement on the wet wall should be the reason for the kinetic energy loss. Well, for this part, we show the SMD. SMD means the salt mean diameter. SMD usually to represent the atomization and the spray. So at for the further locations, such as 20 and 22s, the diameter become larger. We can see it can infer that when the impact on the walls, the secondary droplets may collide or coalesce into larger ones at the near wall region. That means for this part, the small droplets may collide and coalesce into a larger one in this part. Then we check the velocity at different velocity directions. So as I show in this part, this is the definition for the velocity directions. So 4 quarters are divided to represent the direction of the droplet velocity as we show. So for this part, in the first quarters, it means the droplet splash of the wall in the first and second quarters, and for the third and fourth quarters, it means droplets impinging on the wall. As already expected, increase the moved locations to the further locations, the droplets velocity decreased sharply due to the energy loss. Well, more importantly is when the droplets at 50 and 70 means the black one and the red one. So we can see most droplets impinging on the wall for the 10, 20, and 30 megapascal. While at the 20 and 22 locations for the blue one and the green one, so most droplets splash of the wall. it means two parts can be separated. For the 15 and 17, most droplets impinging on the wall, while for the 20 and 22, most droplets splash off the wall. Next, we want to analyze the droplets at droplets velocity at x and y directions. So for the y direction, for the y part and 10 megapascals locations, different locations are shown in this part. We can see the velocity at the y directions decrease sharply, and at these locations, at the 20 locations, the velocity reversal may even occur in this part. While increase the injection pressure to 20 and 30 megapascals, similar tendencies can be seen that the velocity reverse can be seen in this part. So it means suggesting that most droplets splash the wall after impacting on the wall, and then increase the droplets diameters and change the droplets velocity. So next, using the PIA method, we want to see the droplets and the droplets behavior clearly at the near wall region in this part, as we show at the location of 17th and the injection pressure 10 megapascal. So we can see not only the droplets collide on the columns with each other, even the core we can see overlapped with each other and collide with each other. So the secondary droplets splashing of the wall and collide with each other and columns into a larger one. Another part is the splashing core structure collide as the droplets impinging on the wall, leading to the core bodies or the height larger than the single droplets. So we can see this is the model we just proposed. So during the impinging on the walls, the droplets may collide and columns into larger ones, and the cross structure may collide into each other and make the droplets become larger than before impingement. The last one is the conclusions. So using the slicers, we can see the droplets behavior very clearly, even at the very near wall regions. And during the not only for the at the spray tip part, but also at the quite steady state. And the observations prove that the cross structure may collide when the multiple droplets impacting on the wall. Therefore, the secondary droplets from the collide liquid structure become larger, owing to the thick rims and the irregular shape of the crown. So the future works, especially the critical splash, the threshold is sensitive to the liquid adherent thickness during the impact. So it is sensitive. It is essential for us to measure the field thickness in the future work, and then we can determine the new splashing threshold to propose the multiple droplets behaviors. So this is our previous work to just mapping our data with the previous threshold. We can see, so this part is our data. So this is the wet models, yarn models, Karas models, and ribbon models. So for this part, there is no limitations, but almost our data can be separated clearly. So our near future works want to get more clearly threshold in this part to separate our data and to get the new threshold for the multiple droplet splashing behaviors. Okay, thank you. And last but not least, I would like to do some of the co-research with the BIT guys in the near future. Oh, thank you very much to invite me to make the presentation. Okay.
Thank you very much, Professor. Thank you very much. This is certainly one area which is some of our collaboration. Droplet system is certainly very useful from our side. Now, I request Professor Sudhirkumar to take BITS-Pilani and I invite I also request other panelists to please their mic so that we can hear properly. Thank you.
So I am audible?
Yes, you are.
I hope slides are visible.
Yes, sir.
So, good afternoon and greetings of the day to everyone. So, first of all, I would like to thank Professor Goel for inviting me for this talk and all participants. A very good afternoon to all of you.
Professor Dubey, if you can bring down your mic a little bit so that we can see your face more properly.
Is it fine now?
Yes. I think let's go on.
So today's topic of presentation is IoT-enabled miniaturized sensors. So these days, as we know, the cyber systems are very, very popular in all domain applications or all area of interest. So in this line, my today's presentations will revolve around 3 points. In that, first I will be talking about miniaturized sensors overview. In that, we would like to discuss about why miniaturization. Then I will be talking a little bit about detection mechanisms that will create a platform for further understanding about the sensors what we have developed in our lab. So in that context, few sensors that we have developed in our lab will fall under the category of colorimetric sensors. So as a case study, I will take 2 examples. One is nitrite sensors for water and biological samples, and another is a nutrient sensors for soil application for agricultural purpose. And further, we will be talking about some examples of electrochemical sensors, in particular for biochemical applications, and also we will highlight some applications where we can sense the analytes from environment prospects and from industrial application point of view that we can call as a chemical sensor. At the end, I will close my session with a perspective of IoT-enabled miniaturized sensors in different applications area where we can look upon for collaboration in future with Hiroshima University or in particular energy lab. So starting my presentation with miniaturized sensors. So the very first question comes in our mind when we are talking about miniaturized sensors, why to do miniaturization? Sometimes we think that to make it portable, that is the only purpose, or sometimes we think to make it fancy, that is the only purpose, but that is not so. This modern community for different diverse applications demands intelligent sensors. Intelligent in the sense of multifunction, intelligent in the sense of robust performance, intelligent in the sense of low cost product, intelligent in the sense of low power, and obviously in these days we are interested about the devices which work faster or at the rapid rate. At the same time, economy is the major criteria where we look upon minimum material requirement and sample requirement. So these are the some features that we can understand at the outskirt of the miniaturized sensors. But when we are looking deeper, we can identify these are the not only the features because of that miniaturization is getting popular these days, but many times we look upon or we go for miniaturization to exploit better scaling effect, because there are certainly or many times we get a very significant or very surprising physical effects in the microchannels or miniaturized domains. So to exploit these new effects, miniaturization is coming into the picture, and that's why it's becoming so and so popular these days. So obviously, where is the application domain? So the application domains relies in the drug delivery, POC, that is point of care and point of source devices, and microfluidics is having a vast application in the biosystems where we look for mimicking a biosystems in the laboratory to do in vitro analysis to replicate the in vivo systems. At the same time, we look upon the improved reproducibility and the cost and performance. So the answer of all these demands or all these queries, either from quest from scientific community, is coming in the form of miniaturized systems. So that's why my today's topic revolves around miniaturized sensors. I try to have some insight over I try to explain some points why we are going for miniaturization. When we develop a sensor, miniaturized sensors or microfluidic sensors, it revolves around certain process. These processes starts with design and simulation process. That is very important and crucial steps in the designing of microfluidic sensors. What should be the dimension? We can't do multiple iterations. So to understand the physical behavior or the physics at the first stage, always we rely over the design and simulation. And our lab is not only doing the direct fabrications and development of the sensors. First we do simulation. When we are talking about the simulations, we have capability of some in-house code development for Navier-Stokes solvers for fluidic simulations. At the same time, we rely also on the commercial packages like ANSYS Fluent and COMSOL. Particularly COMSOL we rely for the multi-physics simulation. The next step comes fabrications. In terms of fabrications, we have capability in terms of 3D printing, photolithography, soft lithography, and also, as Professor Goel has mentioned in his presentation, we have clean room facilities. Then detection mechanism is also an important aspect before starting the design. So there are variety of detection methods do exist that is compatible for microfluidics or miniaturized systems. In the next slides, I will be talking about them. So, and then finally, once we have the systems, the idea is to test it or characterize it, whether it is fulfilling the desired criteria or not. Initial characterization of individual components is also an essential component. Finally, at the last but not least, these days data management or IoT integration is a very essential component if we talk about the smart sensors or miniaturized sensors for modern community. So I will devote a minute, or we can say 1 or 2 minutes, talking about modeling simulation process chain. So when we say modeling and simulations, to replicate the physics, most of the times we rely over the classical mathematics tools in the olden days, and physics is captured through the mathematical equations that we call mathematical model. But these mathematical models solving in classical mathematics for practical situation is not only in many cases it is not practical, but in some cases it becomes almost formidable to do. So in order to minimize these difficulties, people started relying over the numerical methods. Though the numerical methods is not as accurate as the mathematical classical tools, but it gives reasonably accurate results, and that is of the practical interest in many engineering applications. So in particular, to do the modeling simulation, we rely over the continuum fluid mechanics. The image shows here the droplet behavior in the microchannel that is simulated in our lab, and that is in the microchannel. That is basically continuum fluid mechanics based simulations where continuum theory is applicable. Sometimes when we talk about the microsystems or nanosystems, the length scale is such a small that continuum theory is not valid. Then we have to move upon molecular approach, and many times we come across a situation where 2 or more than 2 physics are coming together, like when we talk about electrochemical sensors or fuel cells, so that is electrochemistry, fluidic, sometimes heat transfer also comes into the picture. So multiple physics has to be simulated simultaneously or together. In that scenario, we use multi-physics simulations. So particularly for the first situation, we have capability to both in-house and commercial software use. But in case of multi-physics simulation, mostly we rely over the COMSOL simulations. So here, selection of the methods depends upon the length scale of the problem. Length scale does not mean the actual dimensions. Maybe actual dimension is millimeter or micrometers, but sometimes the dimensions across which the physical phenomena is changing is varying from a very small dimensions to a large dimensions. So length scale means here the dimensions at which the physical phenomena is changing. Like we can take an example of a system where we are continuously making hydrophobic and hydrophilic systems. So alternatively, a small patches can be created like this, and this small patch, though the dimension of channel will be something different, but a small patch will behave like a length scale parameter for that particular simulation. So this will govern the type of simulation that is selected for a problem of interest. Then we will be talking about what kind of microfluidic systems use detection systems. So detection systems can be broadly classified into 3 categories: optical, luminescence, and electrical. Where optical colorimetric image processing, chemiluminescence, bioluminescence, and impedance and amperometric systems. Whereas this luminescence, chemiluminescence, bioluminescence is a subset of chemiluminescence. If it is having an in vivo system or biological system, we call it as a bioluminescence. So in particularly the colorimetric system or chemiluminescence systems, in both area our lab is working, as Professor Goel has pointed out. We have capability to develop sensors in colorimetric technology. At the same time, we work in the electrochemistry domain also. So particularly now the next point is to understand what I mean by saying IoT enabled sensors. So this block diagram gives pretty fair idea about the IoT enabled sensors. A miniaturized sensor which has connectivity with the IP access device, and finally this IP access device is having connection with the mobile, and mobile is connected with the cloud, and cloud is connected to again back to the mobile or the different elements. This makes a complete circuit of IoT enabled systems. That is a demand, or that is a requirement of modern society to have such kind of systems. Obviously it involves not only microfluidics or the electrical science or electrical engineering or mechanical engineering, but involves a lot of computer domain knowledge in terms of data security and network analysis. So why do talk about IoT enabled sensors? So the IoT enabled sensors having a diverse application area, be it smart cities, be it smart farming or industry or healthcare systems, where we society demands for point of care or point of source devices. Maybe it is a smart homes, and it has also application in the military domain or military area. So it is very difficult to identify in which area the IoT enabled sensors is not suitable. So looking to this diverse application, our lab is also working in some area like colorimetric sensors. One sensor it is being developed in our lab. So mainly this work has been done by Mr. Sohan Dudla. He is the scholar with us in our lab. So there we are talking about the nitrite sensors. So nitrite sensors, as we know, the nitrogen is prevalent in the environment and physiological systems, and it is a crucial component. So sources of nitrogen is inorganic fertilizer, high solubility of water make it feasible that water get contaminated or with the high quantity of nitrite or nitrate. It also reacts with the grounds and sources. These are the sources. Then why to sense it? So basically it has adverse effect if it is having beyond the limit in a particular sample. Maybe it is a biological sample, water, or even in the soil applications. So first we will be talking about, just like an example, nitrite in the saliva is indicated of urine, the oral health, whereas nitrite in the urine in sample can be considered as a biomarker for UTI infection or UTI infections. So to have a sensor to sense it and make it IoT enabled, we started with certain process. I may be a little bit fast to identify the dimensions. We have done first simulation. Mold is being created with the help of and PDMS channel, as it is demonstrated in the picture, is created here, and through mold is created through the FDM process, and we have a 3-layer microfluidic channels in which top we have a PDMS channels, then there will be a adhesive tapes or adhesion material and PMMS sheets. So this 3D microfluidic channel is having one zone where you can say this is detection zone. So this is based on the grease reagents. So when we pass a sample which is to be sensed for the presence of nitrite, or not only for presence but quantification, it gives different colors, pink color, and the magnitude of pink color is directly related with the intensity or concentration of nitrite in the sample. But if you are doing the image analysis, that may not be more accurate. So to avoid this scenario, we have used photometric detection, where we have used LED or photodiode, where the photodiode was selected in such a way that irradiations and voltage come across the load resistance is an indicating value of the intensity. And to minimize the circuit noise and at the same time amplify the signals, we have designed in-house circuitry for this amplification circuit, which is being PCB fabricated using negative dry film photoresist. So by using these systems, we are able to get the data where absorbance is correlated with the concentrations, and this data is being transmitted to the mobile app through the connectivity Bluetooth and off-shelf microprocessor. So this is initial work. Then we have moved upon to extend this system to soil testing, and in soil testing I will be a little bit fast. So this is a whole systems which is having capability to sense nitrite in the soil sample, at the same time pH electrodes. It also gives about the electrical conductivity. So this is the microfluidics multiplex channel, and here also we have used similar principles of working, and finally we are able to get a IoT enabled miniaturized sensors where data can be transferred from sensors to the mobile phone, and it can be having capability to transfer to the cloud and again back to the different peripheral devices. So in this line we have also, our lab is also having capability to work in the electrochemical sensing. So particularly what work I am presenting today is being done by the J. Murli Mohan, who is PhD scholar in our lab. So what is electrochemical sensors if I say in brief? So basically electrochemical sensors are having mostly rely over the 3 electrode systems, where the 3 electrodes are namely called working electrode, reference electrodes and counter electrodes, where the working electrode is an important component because the surface morphology of working electrodes governs the redox reaction, and the peak values of the redox reaction is the indication of a particular analyte presence or quantification of concentration of that particular analyte. So to do this, we have to do the electrical amperometric studies, and for that mostly we use potential state. So potential state is basically a kind of open circuit in the form of circuitry. It is an open kind of systems where usually described in terms of simple open. So presently we are using lab-based open potential state, but also parallelly we are working to have a miniaturized potential state. So, hello, Professor Goel.
Yes, please carry on.
Yes, sir.
Okay. So in that line we have also sensors which can be used for different biosensing applications. So we have interference-free sensing capability through our sensors, where we can sense absorbic acid, dopamine, uric acid, and xanthine. Particularly, these are some points which highlight what is the motivation to select these biochemicals for a electrochemical sensor application. So particularly these slides are explaining how we have fabricated miniaturized 3 electrode systems on PMMA. So where the electrodes are basically Torre paper or carbon fiber papers. So these carbon fiber or Torre papers are basically having inbuilt nanotubes which easily transport analyte and gives a very good electrochemical activity around surface electrochemistry around the working electrodes. So most of the times we try to use a substance which can be used as a working electrode in the simplified or natural form to avoid the surface modifications. But sometimes when it does not work or it not giving a significant redox speed, we modify the surfaces with immobilizations of different other chemical components or chemical compounds. So this is what I am saying, it is having inbuilt diffusion layers, carbon fibers. So as I mentioned, in most of these electrochemical sensors, we rely over the voltammetry applications. So the variety of voltammetry activity can be performed depending upon the sensitivity and selectivity is required for that particular analyte. So like here, cyclic voltammetry results are being presented for typically dopamine sensing, absorbic acid sensing, and in presence of PBS with comparison to the PBS solution. So it basically we perform scan rate and calibrate it against the different concentration, and always try to develop a sensor where it is working in the linear range. So these are some results. I am not stretching much over this, but at the time when we are dealing with the multiple analytes, we try to have interference-free studies. So that is also essential part and partial part of the systems. So similarly, we have also developed a system. I may be a little bit fast. I will go to for an example of hydrogen sensing, which is paper-based systems, and it uses counter electrodes of a carbon paste, and there will be working electrodes and at the same time reference electrodes. So working electrodes, we are using graphite working electrodes. So a droplet of hydrogen can be sensed within this particular device, which is very, very important because the leak detection of hydrogen is not only important for space application, but it is very crucial for industrial applications also. So in this line, we have also worked for detection of hypochlorite. There are many examples, but because of time constraint, I will limit myself to this only. So here also in the same way, we are able to develop a system which can detect hypochlorite, which is these days are very commonly used as a disinfectant, surface disinfectant in multiple applications. So finally, I would like to conclude my presentation with what capability we have, in what area we can work, and then I will close my session. So basically, we have capability and we have demonstrated to develop a colorimetric sensor that is photometric based detection. It is more sensitive, it is not directly colorimetric for chemical and biosensor applications. We also tried to do some work in the water quality monitoring systems, and in POC and POS devices, we have capability to develop biosensors and diagnostic applications. At the same time, we are also trying or moving forward to have sensors which can work for the smart agriculture sector. In future, we are looking forward to collaborate with the Hiroshima team to work in the gas sensing, maybe it is for industrial applications or engine applications. At the same time, our interest is to work upon a lab-on-chip system for conditioning monitoring applications, typically for lubricating oil, where we can realize a miniaturized system for detection of particles by maybe impedance-based study or capacity-based study. As Professor Goel mentioned, already we demonstrated miniaturized viscosity meter systems. So these systems can be utilized for in situ monitoring of different contaminations or different conditions of the lubricating oil. So with this, I will close my session. I will be happy to answer your questions through the chat. Thank you, Professor Goel.
Thank you very much, Professor Dubey, for enlightening us with various aspects of IoT-enabled micro devices. So I think with this, we would like to conclude the presenters in the sense that all the talks are over now, and one way is that we can request the audience if they would like to ask any specific question. I request attendees to please share your questions if you have any. Otherwise, we move on with the next agenda item, which is the